This is just a short video on the properties of an ellipse. Now, an ellipse has a few features that are kind of cool. First off, it starts off with these two fixed points called foci. And generally, we're going to be looking at the distance from these 2 points to any given point. And one of the main properties of an ellipse is that these two distances have to add up to a constant. So in other words, here I have it set up that the two distances, 2.01 and 3.99, are always going to add up to 6. So one way of actually doing this by hand is to put a pin into cardboard in 2 different locations, take a loop of string that does not stretch, and pass it through those 2 pins in the board, drag a pencil up into one corner, pull it really taut, and as you keep it taut, drag the pencil around the piece of paper. And what will happen is the piece of string, since it does not change its length, will keep D1 and D2 a constant of 6 units in this case. So we'd get this shape, and this shape is literally called an ellipse. So that's one of the neat features of ellipses. A couple other ones that you might need to know. Let's see if I can get this to work. Are 2 pieces. One is called the major axis. The major axis generally goes the long length of an ellipse. It has to go through the foci, the focuses, and we call this the major axis. So it has to go through the foci, and it does touch from one end of the ellipse to the other end. The length of this major axis, if the answer here is 6, the sum of the 2 lengths from the focus to the curve itself, literally does become the major axis. And of course, half the major axis would be 3. So there's 3 to the right and 3 to the left, and that'll come in handy later. Besides the major axis, there's the minor axis. The minor axis goes vertically, or from the topmost point to the bottommost point through the center. You can think of it as like the center of the circle. But it does not go through the foci. Alright, so where the major and the minor intersect, this is called the center of the ellipse. And there is a relationship between the center to the focus, the center to the edge of the ellipse along the major axis, and the center to the top of the ellipse along the minor axis. So let's see what happens if we change a few things. If I move the foci, let's see if I can get this clear. Okay. So let's see what happens if we move the foci in different directions. Here I'm just going to turn on the curve instead of tracing it out. So here we have the setup I had before, and if we take the foci and bring them closer together, you can kind of see what happens. The ellipse on the major axis almost becomes the same as the minor axis. And when the foci land on top of one another, you get what is called a circle. Alright, as I pull them further and further apart, the ellipse becomes elongated. It's going to take a long time to get it really thin, but we can elongate this forever, which is kind of cool if you think about it. So by manipulating just the foci changes the shape of this ellipse. But that relationship that D1 and D2 have to add up to a constant never changes. So as I move the D around, that 7.68 stays exactly the same for all these points along the curve. Alright, before we move on to the algebra part of the ellipse, there's one thing to notice. The distance from the center to the foci we're going to call the distance C. And the sum of these two D's, we want it to be a specific number. And that specific number I want to come up with by showing you what happens if we drag this right down to the x-axis. Now remember, d1 plus d2 has to equal a constant. So when I get it down here, you'll see that d1 here is overlapping that length with a part of d2. So what we're going to do with that overlap piece here as a number, because it's going to disappear when I bring it down here, and it's going to look like D1 is just this little segment and D2 is between the foci, but that's not true. There's a piece of D2 that goes from the edge of the circle back to the focus. So I'm going to kind of mentally take that piece and shove it here at the other end. So when I get D1 plus D2, it is literally the distance along the major axis. And that's going to help us in our algebra. And we're going to call this distance from here to here capital A. So 2A would be the distance between, or of the major axis. So D1 plus D2 is going to be the length of the major axis. And that's going to become important in our algebra piece. So now that we have that D1 plus D2 is the length of the major axis, this distance here along the x-axis from the center to the foci, we're going to call that distance C. And we are going to take the distance from the center all the way to the edge of the circle along the major axis. We're going to call that distance A. And in the previous little short, I showed that if we drag this point down to the x-axis, that we have that overlap piece. So the sum of D1 plus D2 is going to be two of these A's. So off the bat, we're going to get D1 plus D2 is equal to capital A times 2. So in other words, the length of the major axis. Eventually we'll come back and talk about this length, and this one actually gets to be called B. And that'll come about after we do our algebra. So here we have some coordinates. This one is d equal the coordinate d x comma y. Down here we have c comma 0, of course, because it's c units away from the origin. And over here we're going to have negative c comma 0. Just writing it a little bit bigger so you can see. Alright, from this we're going to set up the distance formula between 2 points for D1 and D2 and do a bunch of algebra to figure out what this formula is going to become. And inside of this derivation of the formula is the relationship between C, A, and B. Alright, so let's shrink the picture up a little bit. We know that D1 plus D2 is going to equal the length of the major axis, in this case 2A. We know that D1 is this length here, so it's going between xy and the coordinate down here of C0. So to find the distance between two coordinates is the change in x squared minus the change in y squared, all square rooted. So we're going to get the square root of x minus c all squared plus y minus 0 all squared, which is just y squared. And then the same thing's going to happen with d2, except when we do x minus c, you're going to get x minus a negative c. So this becomes x plus c squared. And these are capital C's, not little c's. And then again, we're going to get y minus 0 all squared, which is just y squared. And this whole thing has to equal 2a. And then the fun begins. We need to solve or remove these radicals in such a way that we can get the x's and y's and the a's all kind of away from radicals. And one algebraic way of doing that is to square both sides, but you can't do it, well, it's not nice to do it in the format it's in now. So what I'm going to do is I'm going to shift him to the right-hand side of the equation and then come up with this. I'll leave these unexpanded for a little bit, easier to write. So we're going to get 2a minus the radical of x plus c all squared plus y squared. All right, and then we're going to square both sides. So take this entire side and square it, which means we're going to have to FOIL it. Take this entire side and square it, which means the radical is just going to go away, which is kind of nice. So over here, we're going to get x squared minus 2cx after we expand, plus c squared plus y squared. And on the other side, when we FOIL, we're going to get 2a times 2a, which is 4a squared. We're going to get 2a times the radical, and then the radical times 2a, and both of them are going to be negative. So we're going to get negative 4a squared, I'm sorry, negative 4a, square root of, x plus c all squared, c all squared plus y squared. First, outer and inner, and now last. So I'm going to multiply negative square root times negative square root, which will become positive. And when the square root runs into each other with the exact same stuff underneath, it'll disappear. And now I'm going to expand that out. So that's going to become x squared plus 2cx plus c squared plus y squared. Alright, now depending on how things are going to move around here, I'm going to shift everything to the left that does not have a square root. So I'm going to move the x squares across. When I do, they're going to cancel. I'm going to move the 2cx across. When I do, it becomes negative 4cx. I'm going to move the c squared across, so that one will cancel. I'll move the y squared across, and that one will cancel. So the ones that go away are y squared, c squared, x squared. Alright, so when I move everything across, we're going to get negative 4cx. When I move the 4a squared over, it'll be negative 4a squared. And we'll get something that looks like this. Negative 4a squared. When we move the 2cx across, we're going to get negative 4cx. Alright, and that's going to equal negative 4a square root of x plus c all squared plus y squared. Okay, and the nice thing about this is now everything has a negative 4, so we can basically cancel that out. And we can divide both sides by a. It'll make this term a little messy, but it'll make this term kind of nice. So if we divide both sides by negative 4a, we're going to get a single a here. It'll become positive. We're going to get c over a times x is equal to, and then we have the square root of this mess. Okay, almost there. Again, we have a square root all by itself, so we can square both sides to get rid of it. After I get rid of the radical, I'm also going to expand out what's on the inside finally. So we're almost done, and squaring this side, we're going to get a squared plus. So first, inner and outer is going to be the product of these two, and a times c over a is just going to leave us c. So this will give us 2cx. And then we've got to square the last term, so that's going to be c squared over a squared x squared is equal to, and expand out the other side, we're going to have x squared plus 2cx plus c squared, expanding the x plus c all squared out, plus that y squared. Alright, does anything cancel? Nicely enough, the 2cx's are going to go away. Let's see, anything else? Nope, that's it. So let's move the x's on one side, and the y's on one side, and the constants on the other. So if we're going to move x's and y's on one side, I'd like to keep these positive. So let's move everything towards those two. He's going to have to move over that way. He's a constant. He's going to have to move this way because I want him near this other x squared. And I'll leave the a squared sitting still. All right. So now that leaves me with a squared, moving him over, minus c squared is equal to, combining these as like terms, we're going to get, what's the easiest way to write this? Let's do a common denominator. So he's going to be a squared over a squared, x squared, and this is c squared over a squared, x squared. So when I put them together, I'm going to get a squared minus c squared over a squared. So a squared minus c squared over a squared times x squared plus y squared. Whew. Almost done. So the last step is this. We're going to divide both sides by this a squared minus c squared. And I might have to finish off to the right here. So if I divide both sides by a squared minus c squared, every single term, I kind of canceled that out, but you'll get the idea. The nice thing is these are going to cancel, and we're going to be left with x squared over a squared, and then over here we're just going to get this messy term. So if I bring this up over here, we're getting to the relationship between a, b, and c here. So we're going to have x squared over a squared. Now remember, 2a is the major axis, so this gives us an idea of the length of the major axis. Plus y squared over a squared minus c squared is equal to 1. This just becomes 1. All right, so to make this look a little bit easier, we're going to let b squared equal a squared minus c squared. And therefore, when we finish this off, we're going to get the standard form of an ellipse. X squared over a squared plus y squared over b squared is equal to 1. And the nice thing about this substitution, it gives us a direct relationship between a, b, and c. Now this is for an ellipse that is major axis along the x if a is bigger. Its major axis is along the y-axis if b is bigger. So it really depends on who's bigger here, depending on who's the major axis. So if a is bigger than b, the major axis goes horizontally. If b is bigger than a, then the major axis goes vertically. Oops. Now let's take care of a loose end. And that loose end is this relationship between b, a, and c. And I've said that this length here is b, but I haven't really proved it. So this is just a small little quick proof of why that is going to be the length of b. So if I put our point on the ellipse way up here, then d1 and d2 are going to be equal because these two triangles will be congruent. So if they're equal and the length, the sum of d1 plus d2, we have already kind of set up this formula to be equal to 2a, then since they're congruent, then the single d1 has to be equal to a. So this side of the triangle has a length of a. We've already decided that the side of this triangle is going to be length of c. So whatever this side is, we can call it b. And we can set up the Pythagorean Theorem. So if we set up the Pythagorean Theorem, in this case, a is the hypotenuse. So this would become a squared is equal to, so it's the hypotenuse squared plus the sum of the square of the legs. So b squared plus c squared. And again, we end up with b squared is equal to, after moving the c squared across, a squared minus c squared. So this distance here from the top point, or half of the minor axis, literally is this letter b. So when I talk about this b, I'm actually talking about half of the minor axis. So a is half of the major axis, b is half of the minor axis. So the minor axis would be b up and b down. The major axis would be a to the left and a to the right. So when confronting a formula or an equation of an ellipse, for instance, x squared over 4 plus y squared over, let's say 25 is equal to 1, then all you have to do is put all your relationships together. Now, it really doesn't matter which one you call a, b, and c as long as you remember which number is important. In this case, the important number is the bigger one, 25. So generally he gets called a because we're talking about a major axis. Even though the formula says x squared over a squared, the major axis is more important. So a here, or a squared I should say, is 25. That leaves the 4 to be b squared. So when we come up with a and b, it's obviously going to be the square root of these numbers. So here b is going to equal 2, and a is going to equal 5. And then we can find the c value, which is related to the foci, by setting up the formula b squared is equal to a squared minus c squared. Now that's kind of messy because we're trying to find c. So another way of setting up the formula is to switch the b and the c. So we're going to get c squared is equal to a squared minus b squared. So I kind of think of it as it's the Pythagorean Theorem, but instead of adding, you're going to subtract. So instead of c squared equals a squared plus b squared, for ellipses purposes, it becomes c squared equals a squared minus b squared. So then we can plug in our numbers a and b, well in this case a squared and b squared, and get c squared is equal to the bigger number minus the smaller number. So c is going to equal the square root of 21, and technically plus or minus it. So let's see how to graph this picture. Now, because nothing funny was done to the x and the y, there's no transformation away from the center, which in this case is the origin. So we're going to start here, but it's not a point on the graph. So the first thing I'm going to do is move a units along the major axis, and the major axis is going to be going along the y-axis. So we're going to go 5 up and 5 down because the bigger number is underneath y. So if we go 5 up, it's off the picture, but it's right about here, and 5 down, it's right about here, this would be the major axis from one end to the other. And the major axis length is 10 because it's double of a. Now b is underneath the x, so that tells you to move left and right. So here we're going to move 2 to the left and 2 to the right. So 2 to the left and 2 to the right. And you try to draw your best ellipse that goes through these points. I try to do it a quarter at a time. If you try to draw it with straight lines, it'll start looking like a diamond all the time. So if you do it a quarter at a time and try to get it to curve, because it's supposed to flatten out like a nice plain landing there. Very hard to get it perfect, but that would be the general shape of this ellipse. And then to get the foci in there, they're not physical points on the graph, but we like plotting them to see where they are because they're the reason that this ellipse exists. So square root of 21, let's see, square root of 21 is about 4.6. So it's approximately 4.6. And that just gives me an idea of where to plot it, but I'm still going to label it according to square root of 21. So 4.6 is really close to the top here. So the coordinate of this foci, I'll call him foci 1, is going to be, now remember we're going up and down along the y-axis, so this is 0, comma, square root of 21. And the other one is going to be way down here someplace. He's foci 2, and he's going to have a coordinate of 0, comma, negative square root of 21. And here is what a graphing program will draw. And it looks a lot better than my hand drawing picture. So 5 down, 5 up, 2 to the left, 2 to the right, and the foci end up being right about there. So that's how you draw an ellipse with the general equation.